Get going. Thanks everyone for coming along. Much appreciated. It's a very good turnout. And I see a number of faces that I haven't seen before, which I think is great. Except you, Dave. So what I was going to do is just a quick 10-minute introduction. This is the same talk that I did very briefly at the previous session, which was meant to be for post-PGG graduates, but so it's kind of a bigger crowd here, and I think it'll be useful for at least some of you, and then we'll get straight into the Meteorology session with Fraser. So I'm just going to zip through this. It's just really kind of introducing people to the resources that the club's put together. I've called it an introduction to the paragliding scene, but we've had this feeling that new pilots have been left to themselves for quite a long time, and we know that there's a very high accident rate in those first couple of years of flying, and even the first 5 years. Part of the purpose this evening is to kind of start bringing new pilots into the fold. The Meteo talk in particular has been structured in two parts. One is kind of for newer pilots, like all the kind of background introductory stuff, and then the next one will be much more on the forecasting side, how to use all that information. So I just thought I'd take this chance to kind of bring you up to speed with other things that are going on. And I think, the thing to really stress about these evenings is that they're a really good chance to meet other pilots and talk about flying. It's a very hard sport to learn on your own. So, the information's one part of it, but it's actually coming in and being part and talking to people, and because there's some really experienced people here who know a lot of stuff. Don't expect to get mentored here as a new pilot. We have a large number of pilots going through the schools here, and the senior pilots just get burnt out if they try and mentor everybody individually. So, you're not on your own, but it's your responsibility to learn how to be a good pilot. People will help you, ask questions, talk to them, but you're the person who's responsible for becoming a good pilot. And as I say, there's a lot of resources and a lot of people who are willing to help. Just, we don't want to overload them too much. So I'm just going to talk first of all about, there's a bunch of stuff that we've put together in the club, and then some stuff that NZHGPA has put together. So from a club perspective, we've got so I'll just we've basically focused on putting together a bunch of information on our website primarily. So chpgc.org.nz, and there's a bunch of things along the top here. So just running through some of the key ones. Weather. There's a discussion about the weather, and there's a couple of other documents that I think Brian and someone else have put together, just describing some of the key weather systems that we see here in Canterbury, and it is a bit different from other parts of the world and other parts of New Zealand. So there's some key features you need to be really aware of. So have a look through that. We've put a lot of effort into flying sites over a number of years. I think Andra started this kind of upgrade of the flying sites, and who started it, Andra?
There was a thing ages ago. We just went for a big update when we were creating the site.
Right, yeah. So there's a lot of useful information in there. You can see each of the sites has quite a detailed discussion, the key things to look out for, the kind of weather conditions. And then in addition to that, we've, Ross and John in particular have done a really good series of videos about the main sites around Christchurch in particular. So there's this one here is we started with the gondola one, and then we did other flying sites around the Port Hills, and then there's the Castle Hill Basin deep dive. So those cover the main areas that you're flying Canterbury, and they're really good sources of information. Like they're really detailed about where to fly, when to fly, and what are the things to watch out for. So I thoroughly recommend those. Hike and fly. So I'll just close that. There's a number of hike and fly sites have been. James has put together a good briefing on those. Particularly the ones focusing on the ones that are good to do your first hike and fly adventures with. So I thoroughly recommend you have a look at that. And then Nick has done this really good look at. So this is the post PG2. So what we were thinking about was, when you come out of PG2, you've done your 40 flights, and you really don't know that much. So this is an attempt to say, here's a way you can look at progressing from those very basic set of skills through to being a kind of reasonably competent pilot. So he's talked about, we put together this guide about what are the skills that you need to fly at a site, and what can you learn at each of these sites. So I think it's a really good effort. Nick's leaving us soon still?
I don't know, probably.
It's a really great thing you've done, Nick. I'm very appreciative of it. Pilot safety. So this is basically goes through and talks about accident statistics, some of the sources for information for thinking about safety, and some Canterbury specific information. And I try and put out some, when we have accidents, with significant accidents, I try and put out some briefing notes on it. So they'll all be collected in here as well. In addition to this, there's NZHGPA has put together a Think Like a Pilot campaign, so that, again, a really good source of information, and it goes through my environment, my plan, and myself, so some key areas for you to think about, and they've developed a whole set of resources under each of those. Bunch of stuff in there. And if you're really interested in the safety side of it, the NZHGPA also put together a safety review a couple of years ago, and that goes through the main sources of accidents. It's useful for all pilots, actually. So that's on the main site under the safety page. So that was really the main things I wanted to say tonight. I had a few key points just for new pilots. But this is just what I observe as the safety officer. I try and debrief with all pilots who have an accident. I think, your first couple of years, high risk, it's not like other sports that you've done. It's very binary, and there's very little feedback in terms of whether you're doing something's wrong until you hit the ground, and then it's really quite hard feedback. I was actually looking at statistics the other day. A friend had a mountain bike accident. We were comparing statistics. So mountain biking, you have about an order of magnitude more accidents than paragliding, but your chances of death are an order of magnitude less. So like 10 times more chance of having an accident, but 10 times less chance of dying. And so you're getting this constant feedback about what you're doing wrong. And I guess the circumstances of accidents are not as serious, whereas we get very little feedback when we do stuff wrong. We can get away with stuff for ages, and then all of a sudden we don't. So you need to be really careful. You need to be really patient about your progression. Taylor's is a great site, so spend as much time as you can there and learn your basic skills there. I know you've spent a lot of time there already learning. You're kind of amping to get away, but it's a great site. Spend your time there and figure out as much stuff as you can. I want to get going, yeah. Just some key points. Don't turn into the hill. We have a number of accidents every year. where pilots turn into the hill for various reasons. Every time, just turn away. Doesn't matter what's happening, turn away from the hill. Be careful of traffic, particularly at Taylor's. We're about due for a serious accident from a mid-air collision there. We also have a number of accidents where people get kind of overwhelmed by strong conditions at Taylor's. Not necessarily that they get pushed back over, but just that finding it hard to get down and things go wrong. So when you do find yourself in strong winds, just push out, push the speed bar, push out onto the hill, and the lift will eventually stop as you go out towards the beach. Beware of the gondola. It's a great sight, but take your time introducing yourself to it. Your first flights there should be in calm, gentle conditions with a nice little breeze coming up the hill. Don't go over there when it's strong, when it's difficult to launch. And stay away from the ground when it's thermic. We just have a lot of pilots hit the ground because they're getting too close in strong thermic conditions. And I think the final point that I've made there is, the culture we have in the club is, it's about being a good pilot, not being, what we think of as good pilot is a pilot who has kind of well-rounded set of skills for what they're flying. So there'll be some pilots who are pushing in and doing, really impressive things. But I think you'll get nothing but support here by recognising your limitations and staying within those and trying to learn within those. I've flown a number of years here, and I fly very low rated wings and very calm conditions, and I've had nothing but support from other pilots. And no one's ever, I've never felt condescended to or anything. So I think that's our culture. It's, we want to support pilots to be good pilots. We're not. Some of the parts of the country are a lot more rah-rah about the flying. Here we just want people to be safe. So look after yourselves. What's that?
It's because you're so cute.
Very good. That's all I had. Fraser.
Cool. Right, it's not that boring. Right.
Renovated pink sweats.
Oh, the lyric got me all Sunday to find a way to that'd be awesome.
That's something with Instagram.
I tried to convince them. That was easy. I tried to convince them to come. Oh, that's
Alright, let's get into it. So, I'm Fraser. I've met half of you. You don't. The rest of you, I'm really good at faces and I suck with names, so I'm sorry if I don't call you out by name. But anyway, so my background, I'm a commercial pilot. I currently fly for Jetstar out of Christchurch. I do the A321s and A320s over in Australia and Auckland and about. Started flying about 15 years ago. Been paid for the last sort of 10 years of that. So I learned in New Zealand, did a bit of flying in Australia, instructing over there, as well as a bit of fire support stuff. Went over to PNG. I've been over there since 2017, flying little planes around the jungle, as well as a couple of the airline things over there. About 5,000 commercial aeroplane hours. So my background is largely in airplanes. This is a photo I took out of my last job, flying out of a mine in PNG. Oh, Dash 8. As for paragliding, I'm quite new. Started learning about 3 years ago. Probably not much more than about 50 hours. So I'm not the paragliding expert. I'm not the person to come to for paragliding flying advice. But the meteorology training that airplane pilots get is significantly more intense than what you'll ever see in a paragliding environment. So hopefully I can pass it on to all of you. Fingers crossed. So this one, as Simon mentioned, we're just going to go through sort of fundamentals, understanding why air is moving, what drives it around, as opposed to staring at a weather chart and sort of inventing what it means. So before I crack on, does anyone in this room have any higher meteorological training than what they did for their PG2? What have you done?
Meteorology and climate for many years.
Yeah, cool. We've got an expert over here, so he'll make me sound really stupid. Fingers crossed. Yeah? Oh, sweet. Yeah, we got a proper pilot. Cool.
Meteorology and PPL, because I was doing PPL for a bit, so.
Right, so we've got a couple of PPL, CPL experts around the room. What about everybody else? Have we got anybody that's never done anything? Cool, cool. Yeah, and that's fine. That's fine. So this is like bare bones. So hopefully we concentrated on you guys. So by the end of this course, these are some things I'll hopefully have a foundation in. Science behind reading the air. So why is it happening? We'll just look at wind. Very important paragliding. What happens in thermals? So understanding actually what's going on when you're flying through these things. A bit about clouds and some bigger picture stuff, if we get time for it at the end. Sort of the bigger factors driving the planet's weather systems. And then the forecasting stuff is going to be another night where we sort of just go through where you can find weather, what's there, what information it's giving you, and sort of what it all means. So this whole PowerPoint was actually designed for a school to do a PG2 meteorology course. So everything in the curriculum was put into this, and I tried to leave out a bunch of the stuff that wasn't because it's just too much. So that's why it says there's going to be no test today. Ask questions, interrupt me, stick your hand up, yell out. The more you're involved, the more you're going to learn. There are some numbers and formulas in here. Yep.
Wrong one.
Yeah, you found it way around.
The other one. Turn this one.
Yeah.
All the numbers and formulas in here, you don't need to know them. When you're flying by the seat of your pants, which you will be doing, you don't need to know these formulas. There's just a couple numbers that we'll use and concentrate on, just so you have an understanding of what's going on. The biggest thing is understanding why the weather's occurring. So I've sort of broken down. It's kind of hard to see, isn't it? There's 6. I call them fundamentals. I sort of went through and worked out what topics I was talking about. These are the kind of the core things you're going to get a grasp of before you look at a weather chart and go, oh, that's what's going on. So heat, why that drives everything. How temperature changes with height. So we're obviously flying up and down. How temperature's changing with height will drive your ability to fly up and down. What dew point is, so where the clouds are forming. What causes wind. The Coriolis effect, why air seems to always spin in circles instead of straight lines. And we'll just touch on the Bernoulli's theorem because air likes to accelerate through little holes, and I'll explain why. So, from the very beginning, you can all take a guess what I'm about to talk about. What drives the weather on the planet? Anyone take a guess?
The sun.
Yeah. So, without that sun, we turn into a cold, dark rock. With the sun, it's like, think about a fry pan with water on it, things start fizzing away, things start happening. So, out of the sun, we get light, but we also get heat. Very handy to recognise they all go hand in hand, because normally where the sun's hitting the ground, you're going to get things heating up. Heat makes air go up. Very handy for us. So that is the absolute fundamental of everything. Without the sun, nothing happens. So the 2 takeaways: if the sun's going to hit the ground, you can expect things to happen. If the sun's not reaching the ground, you can expect things to calm down. How that's relevant to all of you, say you're at the gondola, it's a cloudy day, it's all very calm, you're having a nice flight. Sun comes out, hits the ground, rocks start firing up, things start getting violent, things are going to change. So the biggest thing is, your sun is your engine. With it, things happen. Without it, generally, things calm down. Questions?
No?
Cool. We're keeping the stuff basic. It does get a little bit more tricky quite soon. So, when you're looking at weather, what you're flying in, you kind of look at 2 different dimensions. You look at sort of the bigger picture, what's going on. You know, is the air changing around me? Is there wind? The other thing you look at is the air vertically, right? So, we can't fly horizontally very far in a paraglider. So we sort of concentrate on an area, and you want to know what's going on from the ground up into the air where you're flying. So this is a cross-section of almost the entire atmosphere. Most of this stuff is irrelevant. All we need to know about is this part right down the bottom called the troposphere. We operate in that. It goes up to an average height around the planet of about 36,000 feet. The reality, that does change. But we're in this troposphere right down by the bottom of the planet, and that's where all the weather seems to occur. And we, as paraglider pilots, are operating right at the bottom of it in the last 10,000 feet. You get up above that, not much actually happens. So we're just going to be concentrating on this little part of the atmosphere today called the troposphere, the top of that, the tropopause. Not very useful to you, but there are a couple of terms that you may just come across, so I'm just introducing them to you briefly. So you may all be aware air up in the sky is much colder than air on the ground, right? Has anyone not come across that concept before? It's usually cold up on the top of a mountain and cold on the ground. So the reason for that is this air column is actually heated from the bottom up. Even though the sun's coming in from the outside, it's coming in at too high a frequency for that heat to stop and impart itself on the air. Hits the ground, heats up. Once it hits the ground and heats up, like you used to it on a sunny day, you touch the concrete, it's hot. It passes that heat into the air from the ground through contact, and then that air here heats up, and then it dissipates as it makes its way up into the atmosphere. We'll go a little bit more into that, but an understanding that there's temperature changes with height will start to allow us to guess, is the air going to be rising or not today? So, things that happen in a vertical column of air. So, this whole first part of this whole PowerPoint is all going to be about what's going on up and down. The horizontal stuff will happen later. So, in that vertical column of air, there's quite a few things that happen. There's no point asking you because I've written them all here. So thermals, does anyone not know what a thermal is? We'll go through how it works, but has everybody heard of a thermal and kind of understand what it is? Cool, so it's generally air rising. It's a location where air is going up. That's generally a thermal. Clouds usually form in the areas, vertical areas. It's because of vertical rising that cause clouds. We'll cover that a little bit later. Rain normally happens because of vertical shifting of air, and you get changes in pressure as you go up and down as well. This is all generally a result of heat rising. So sun hitting the ground triggers a lot of things that cause all of these things. So we'll go through and look at why. This is once again going back to the absolute basics. As a general rule, cold air will sink and hot air will rise. So this is stuff you get taught right back at school, hopefully. The difference in temperature between the air that's rising and the air beside it will determine how fast that air goes up. Say you've got a rock. That rock has heated up what was 15 degree air up to like 30 degrees. That's 15 degrees. It's quite a big difference in temperature. That air that's been heated is going to rise really fast. But if that air's only been heated a small amount, 2 or 3 degrees, if it rises at all, it's going to rise very slowly. Does that all make sense? Cool, lots of nods, this is good. You're not falling asleep just yet. So there's just a couple basic things to take away there. Hot air tries to go up, cold air generally tries to sink, and the difference in temperature will determine how fast that air moves. So this is where it gets a little tricky. Now I put the hardest thing at the start, hopefully while you're all awake, and then some of the more interesting stuff at the end when you're hopefully it'll keep you awake. So lapse rates. Has anyone in here not heard of a lapse rate? Cool. That's normal. This isn't stuff that they teach at school. Well, I didn't find it at school anyway. So a lapse rate refers to how air cools or warms up as it goes up or down in a column. There's two fundamental terms here, and once we get a grasp of these two terms, the rest of the next bunch of slides will make a lot more sense. So one kind of lapse rate we have is the environmental lapse rate, and the other one we'll talk about are the adiabatic lapse rates. When you understand these, you'll understand how lift works. So the first, the environmental lapse rate. So what you're thinking about there is, in your vertical column of air from the ground to the sky, how the air is cooling down like I spoke about before. So we say on average the air cools down at about 2 degrees every 1,000 feet in elevation. I'm a feet for height kind of person, not a meters kind of person. If you're a meters person, I'm sorry. I've worked a couple meter things into here, but generally I'm going to talk about feet, 3 feet to a meter. If you're struggling with it, just speak out. We can work on things a little bit more. But basically, the environmental lapse rate I want to talk about is, so on the ground, if it's 20 degrees, every 1,000 feet you go higher, it's 2 degrees colder. Now, that environmental lapse rate doesn't mean air rising. It's just the stationary air. So on the ground, it's 20 degrees, 18, 16, 20, every 1,000 feet you go up. The adiabatic lapse rate is how air cools down when it's grabbed as a parcel and lifted. So I have a little training aid. I'm going to do a bunch of weird things with this sponge today. Here we go. This early on is probably not good. So this parcel of air, as it goes from the ground and rises because it got hotter, will cool differently than the air that's stationary beside it. So think of an air column over here, the environmental air that's not moving, it just feels colder as you go higher. Then this, my adiabatic air that started at the ground, as it rises, it will actually cool at a different rate. What's happening?
Because of the higher temperature?
Because
The difference between that.
so what's going to happen? A parcel of air has a whole lot of weight on top of it, right? From all the air above it, it's compressing it to be a certain weight. As it rises, there's less air above it. The pressure comes off that parcel and it will expand. As it expands, it's like spreading butter. It gets thinner and thinner and thinner. That is the heat. So it started off really small, it rose, it expanded. The heat in that package, as it expands, cools off. Same piece of parcel, now it's bigger. So that cooling, as it expands, is the adiabatic effect. So with that, there's a couple of numbers. And this is the formula part. These numbers are the numbers that matter to understand what's going on, but you don't really have to understand them. We use pictures to sort of describe what's actually going to go on when we get to RASP charts and stuff later on. So the first one, we spoke about the environment that gets colder by 2 degrees every 1,000 feet. Now this isn't a hard and fast rule. This is just an average. In reality, it does all sorts of crazy things. But the adiabatic lapse rate is broken down into 2 different temperatures, the dry and the wet. So air that's dry is referring to air that's not a cloud yet.
Say that again?
Air that is dry is referring to air that's not a cloud yet.
Right.
So air inside of a cloud is called wet or saturated. Air that's dry is referred to as dry. So
Compare it to a blue thermal as well.
a blue thermal,
Yeah.
I don't know what you're talking about.
Like thermals no moisture in it, so the thermals going off but they don't condense to form clouds.
Yeah, so
They
the-
call them blue thermals.
Right, yeah, I just haven't come across that term.
Okay.
Yeah, so we can incorporate that actually when we get to the thermals part. So the dry adiabatic lapse rate, as this air that's a parcel that's being lifted, we'll actually cool it 3 degrees instead of 2 degrees. Every 1,000 feet it gets higher. So it's actually cooling down faster than the air beside it. So remember over here, the environment constantly getting cooler. Well, this air, as it's raised, will cool really fast, 3 degrees every 1,000 feet. And that is pretty much a fixed amount. It never really changes. If it's wet, so it's in a cloud, it cools a little bit slower. So before I explain this other cooling rate, I need to introduce something called dew point. And then we'll just spiral back to that last part. So this is the most complicated part of the whole night. If you're getting lost, just shout out. It gets much easier after this.
Hang on. So when you talk about that wet adiabatic collapse rate,
Yep.
you're talking about air in the cloud.
Yep.
Gotcha, that's what I need to know.
Cool. So we're going to spiral back to that, but we need to first understand why it's becoming a cloud
Yeah.
in the first place. So there's a thing called dew point. Has anybody not come across dew point yet? I'm going to take by the silence and no nodding that probably yes. So dew point refers to the temperature of air as it cools down, that air starts to condense moisture. So here we have 3 slides. Once again, the sponge. This sponge, the size of the sponge represents how warm a piece of air is. The ability of air to hold water is determined by its temperature. So really hot air can hold heaps of moisture in a gaseous state. Really cold air can't hold much at all. The temperature where that air cools down till it can't hold any more water and then it starts to squeeze it out is called dew point. So this is where things are going to get weird.
Is that the same as humidity?
Humidity is...
If you get 100% humidity, you talk about saturation point?
Yep, that is the point where the air gets 100% saturated,
Yeah.
is the dew point.
Gotcha.
So this kind of worked at home. Hopefully it works today. So we're going to use crazy numbers just because they're easy. So imagine we've got air, and that air is 100 degrees. At 100 degrees, that air can hold all of the water. If that, so say the air that was 100 degrees was a third full of water. So disregard the dripping water coming out of this. A third of this sponge that is 100 degrees is wet. It contains about 1/3 of moisture. The dew point will be 33 degrees because I can cool this air down. There's about half, don't worry about that, that's not coming out properly, that is still holding the water in it. It gets to about 1/3 of the size, it's still holding water, but as it keeps cooling more and more below a 30%, that water starts pouring out. So that temperature, that the water starts really pouring out, is the dew point. So when you're talking about relative humidity, that is the percentage of the air at that current temperature holding moisture. So 3 packets of air, all holding the same amount of moisture. 1/3, 1/3, 1/3. This is yellow circle represents the temperature. If it's really hot, it still holds all that moisture, no worries. It shrinks, it can still hold that moisture. When it shrinks to the point where the temperature and the moisture become the same, that's the dew point. If it cools any more, water will start to come out of the air and form a cloud. Questions? Cool. So one thing to take away from this is water that you see as a cloud is liquid water. Water that is a gas is invisible. So this room right now is full of water in a gas state. If you could see the condensation like fog, mist, cloud, that is water. When this air reaches dew point and starts to squeeze itself out, a couple of things happen. First is the air that was, well, the water that was a gas is converting to a liquid. It's coming out. But for it to do that, for it to go from a gas to a liquid, it has to release a whole lot of energy it was holding to be a gas. That energy that it releases at the same time as it releases water is called latent heat. That heat comes out and just heats the air parcel that it's surrounded by. So we're back to Our air packet, it shrunk, it started squeezing out water. At the same time, it also jettisoned heat, and it poured it back into the sponge.
And it what?
It put that heat back into the sponge.
And it expanded?
Not quite,
Okay.
but it offsets the cooling that it was doing. So this is where I'm spiraling back now to our previous point. This wet adiabatic lapse rate, the way the air is cooling as it's rising while it's wet, so that it's now squeezing the moisture out, making cloud, it cools down slower. So it was cooling at 3 degrees. Every 1,000 foot it went higher, but now it's got this latent heat going into the equation, heating it back up. It still cools, but only by about half as much. So that's why we say the saturated adiabatic lapse rate, how much that air is cooling down, cools down at 1.5 degrees every 1,000 feet instead of 3 degrees every 1,000 feet.
Because it was not as hot as what it was when it started, so to speak.
Yeah, it was cooling down
Yeah.
really fast.
Yeah.
Then the water started coming out, and the
Yeah.
rate that it was cooling down just slows down a little bit
Yeah.
because there was heat being reintroduced.
Yeah. And that's just carry on from dew point
Yeah,
further.
yeah, until it squeezes itself dry. Questions? Right. So this is an absolute fundamental to understanding if you're going to get lift or not in a day. So we're going to go into that a little bit deeper. Now, this is just a bit of a visual representation here. Now, I stole all of these images straight off YouTube, Google. So I don't claim rights to any of them. That's why some of them have weird numbers on them. This one, I actually quite like the hand meters. So those of you who like meters, this one actually incorporates. Now, these represent our environment, our environmental lapse rate, just how cold air feels as it gets higher. It also represents our wet adiabatic lapse rate and our dry adiabatic lapse rate, how air is cooling as it's being lifted. So this blue line is our environmental lapse rate. On average, 2 degrees every 1,000 feet. 8 degrees every kilometre. Thank you, person from Google. This line represents a wet adiabatic lapse rate, so water that's in a cloud. It's cooling as it gets higher. So here's our temperature and here's our height. It cools, but it actually stays warmer than the environmental air next to it. And here we have air that's cooling while it's dry, the dry adiabatic lapse rate. It cools much faster than the environmental air next to it. So you can look at this and go, okay, will this air rise or not through heat? Well, as it's gone up, it's become colder than the air beside it. It's not going to go up anymore. But while it's rising and cooling, but it's cooling at a rate where it stays warmer than the air around it, it will continue to rise. I'm going to go into much more detail on this again a little bit further on because this seems to be what everyone's interested in. Now, this, I'm only going to touch on this very briefly because this is more of forecasting stuff, but this is a RASP chart. This is what I personally think is the easiest way to actually see what's going on in the atmosphere. So this is just, once again, temperature along the bottom and height. And you've got a couple lines here. The red line is an environmental lapse rate. So this is what the air actually does as it goes up. Sometimes it gets warmer as it goes up. Sometimes it gets colder. Sometimes it gets cold really fast. Here it's getting cold really fast, warming up a little bit, and then cooling really slowly. Over here, it's not even cooling down as it gains height. It's just staying hot all the way up. There's a bunch of other lines on here. There's yellow lines that represent our adiabatic lapse rate, lines that are green that represent our wet adiabatic lapse rate. So this is a chart we'll come back to, but the reason I put this stuff here is just to show you guys, even though there is this standard environmental lapse rate, these standard adiabatic lapse rates, what it really does is all sorts of crazy zigzags. And you'll use these charts to go, okay, so the air at the ground got heated to about 30 degrees, and it's going to cool down at this environmental lapse rate, but it's going to stay hotter than the environment around it. If it does, you're going to keep getting lift. If that air intercepts the line, like over here, so the air got heated up to 30 degrees, it goes up, but eventually it hits the environmental air temperature, it's no longer warmer than it. It stops going up. So I'm going to go into this in much more detail on the next night, and there's a really, really good YouTube video about this stuff. But without understanding that environmental lapse rate and that adiabatic lapse rate, you can't understand this. So that's why I brought it in today. We've got a bit of a thermaling thing at the end, just explaining thermals, where hopefully this will get a little bit more cemented in. So, just to recap, even though it's written on the board, can someone tell me why there's an environmental lapse rate? Why does the air feel warm at the bottom and cold up at the top? Anybody want to throw out an answer?
Heated from the bottom.
Heated on the ground.
Yeah, that's right. Air is all heated from the ground. When there's clouds, sometimes the sun heats those up as well, but if it's just clear air, the sun doesn't heat up any of the air, it heats up the ground, which then heats up the air from the ground.
Hey, Fraser,
Yeah.
what about if you got to your settings and you turn the brightness down? Would that help?
With the environmental rate.
The moisture and all that?
I don't know, it's just a predictive
Oh,
control.
right. I mean, if it's sort of that easy, don't worry about it. I just thought it might be an easy thing to do.
It's white on white. It's not going to help.
Yeah, I'm just sort of thinking.
Yeah, it's okay if you could sound like a PowerPoint into a group chat, maybe.
Yeah.
Yeah.
Did you see it bottom
Um, most of these words are sort of meter prompt anyway. So, that dry adiabatic lapse rate, why is that air cooling at a different rate as it rises? Can anyone want to take a punt at what an adiabatic lapse rate is?
You said there'd be no test.
Yeah. This is just me making a thing to try and make it stick in your brains.
Particle expanding.
Yeah, that parcel expands, and therefore it cools as it gets lifted off the ground. Air can rise for two main reasons. One, the heat from the ground heats it up and it starts to rise. The other one is it can hit terrain as it moves over it and it can be forced up. Both occasions it cools in the exact same way. It expands, it cools off. It can reach dew point and become cloud as it goes up. Sometimes it does, sometimes it doesn't. Depending
Fraser,
on...
you might want to mention a couple of points. One, the sun doesn't emit heat, it emits energy which Earth turns into heat. And it's the ground that provides the heat
That's right.
rather than the sun. And the other is adiabatic. An adiabatic parcel is non-diabatic. It doesn't exchange heat with its surroundings, so it stays as an entity on itself.
That's right, that's right. So what he's saying there, the adiabatic parcel doesn't exchange heat, so that parcel that's rising isn't mixing, it's staying as a parcel. Think of it being in a box. As it goes up, that box will expand and cool down inside the box, but it's not actually mixing with the air next to it. Sure, on the edge you might get a little bit of mixing in real life, but when referring to adiabatic stuff, it's referred to as a closed parcel.
View, it has the meaning that, like, it's just intellectually it doesn't exchange heat.
Yeah.
It does actually, but...
Yeah, it's very complicated.
Right.
Yes.
Does that mean that it's cooling purely because of the rise and not necessarily because of the external temperature being lower?
Whether that air is going up or down is because of the difference between its parcel and the temperature of the environment around that parcel. Yeah. So if it's warmer than the environment around it, it goes up and starts to expand. If it's colder than that air around it, it goes down, and if it's the same temperature, it just sort of stays level. Is that what you're getting at?
No. No, that's my meaning. If it doesn't, if it expands as it rises, and it's not necessarily cooling because it's mixing, is it just cooling because it's more surface, like theoretically surface area of the expanded parcel, or volume, or is it because it's actually just rising in height?
Yeah. So if that parcel was given another reason to expand,
yeah,
it would still cool as well.
Okay.
Yes, it didn't have to rise, but generally it's expanding because it's rising and there's less above it holding it and compressing it.
The word adiabatic means not exchanging energy with through its boundary.
Yeah.
So it's only due to expansion.
Yeah.
Cool.
And it expands because the pressure of the air gets less with altitude.
That's right.
So
Can I ask you a clarification as well?
Yeah, go for
Put
it.
it in mind, does that mean the adiabatic kind of lapse rate is kind of the idealized perfect situation, maximum
Yes.
situation that you measure against? So that
Yeah, so a lot of this, there's this thing called the standard atmosphere, and all these weather terms are all based on this perfect world. Like we say, the surface temperature on average is QNH 1013, the average temperature is 15 degrees. The thing cools at 2 degrees every 1,000 feet, when in reality it does not. It does all sorts of crazy things, but on average, everywhere we say it's these values because it helps us make sense of it all. So that cooling of 3 degrees as it expands and goes up is generally a pretty fixed figure. The environment cooling at 2 degrees is absolutely not.
So the big picture way when I learnt years ago, you take the nor'wester in Canterbury, and you've got the westerly blowing across from the west coast, full of moisture. Hits, say, just for example, starts raining at ground level, goes up 10,000 feet. So if it's 15 degrees when it hits the start of the mountains, goes up 10,000 feet, it's going to drop at 1.5 degrees as the moisture comes out of it.
We've actually got that in here.
Oh, and then
Yeah, the
it
foam
comes
wave.
down the other side, and because all the moisture's gone, it's coming down as dry.
Yeah.
It's coming down and it's warming up at 3 degrees, so you end up with a 15-degree differential. So it's 15 degrees on the west coast and it's 30 degrees on this coast.
That's right. So he's referring to something called the foam wind effect. Some people call it the Chinook wind. Mountain ranges will squeeze all the moisture out of the air, heat it up, and give it to us on the other side, much warmer and much drier. I've got that a little bit later in the PowerPoint, which is good. He's bringing it now because it all ties together. So meteorology is just a big whole lot of spaghetti with a whole lot of facts. You kind of have to work them all together. As much as I have tried to put it in some sort of structured order, it all just goes back and forth on itself. So we're going to move on from the lapse rates, unless there's other questions now, and then we'll tie this all back together when we actually look at thermals and stuff just a little bit later on. So we've talked about all that. So to recap from that bit we've just talked about, one is air becomes colder when you gain height. That's called the what lapse rate? The environmental lapse rate, that's right. The air cools as it rises at a fast rate. So air that's rising cools at a fast rate. That was the adiabatic lapse rate we keep talking about, the dry one. If it gets as cold as the dew point, water starts coming out, it will cool at a slower rate. And I've just written there, you can barely read it, the real environmental lapse rate, as we saw, changes a whole lot, and that's what actually determines whether this air is going to keep rising or not. So, real world scenarios. That was probably this is the worst part of the whole night, getting that into your head. We'll just look at some more real world stuff and hopefully tie it all together. So, the environmental lapse rate can be steep. If I say the environmental lapse rate is steep, that means it's cooling off really fast. If the environment cools down really slowly as it gains height, that's a shallow lapse rate. If it actually warms up as it goes up, that's an inversion. Has anyone here not heard of an inversion? Lift killing things. Really hard to fly through inversions because they just get hotter and hotter, so air rising is never hotter than the air above it and it stops going up. There's also something called isotherm, which we'll look at in the next one, which is just air as it goes up, staying the same temperature. Isothermic, iso means not changing. So we'll just look at this in a picture format. So this is like a normal scenario. This line represents the environment and the environmental lapse rate. There's some crazy different numbers in here because once again I took all these pictures from Google. So this line is getting colder at 2 degrees. Every 1,000 feet it goes up. This is our dry air. So say the air on the ground got heated by a rock to about 20 degrees. As it rose, it cooled off really, really fast. And it's either going to meet the environmental lapse rate and stop going up, or it's going to condense into cloud, and then it's going to cool down slower. So we've kind of flogged that one at this point.
Oh, yeah.
There's another term, I call it unstable. So unstable air is air that is rising without anything stopping it. So a situation we're going to get air rising and not stopping is when that air, even though as it rises, it never cools down to the point where it's the same temperature as the environment beside it. So say the air is rising, it got really hot, it's cooling. But if it stays warmer than the air in the environment, it's just going to keep going up and up and up. It's going to condense into cloud at some point. So say here it condenses into cloud, and then it just keeps going up, because now it's cooling even slower, and the difference between that temperature of air and the air beside it is now getting even more separate, and it just goes up and up and up into space.
CB.
Yeah. Yeah, so not a good place to be for any kind of aircraft at all, really. But this can happen on a small scale as well. So we might be looking at a chart where the air is not meeting the environment, but up here the environment might start getting hot again, and it will eventually stop. But if it's completely unstable, it'll go all the way up to the top of our troposphere, hit the tropopause before it stops. Remember, we're only flying at up to 10,000 feet. That atmosphere goes up to 36,000 feet. So that's where you get paragliders into situations where they get in clouds, they start getting lift, they get taken up into so high in the atmosphere they can't breathe and they pass out. And you get those crazy videos. Yeah.
Question kind of related to the last slide where the saturated adiabatic rate was non-linear. Can you infer, I'm assuming that's because
so
the
that
saturation decrease, well, like the water density decreases.
Yeah.
The bit I'm curious about is when it intersects the dry adiabatic lapse rate again, is that when you reach the top of the cloud, or is that not something you can infer?
Whether the cloud stops or not is generally where it meets the environmental lapse rate.
Right.
But the amount of water getting exhaled by that air parcel as it goes up, it does start to dry out. There's much less of it. There's much less energy being squeezed back into the air. Remember I talked about every time moisture comes out, heat comes out with it? If there's less moisture coming out of that because it's become very dry, there's also much less heat coming out. So that 1.5 degrees does steepen back up and start cooling down faster again. But that happens on a very tall scale, enough that you don't really need to worry about it in the paragliding world, even in any world, really. Once you're starting to deal with forecasting what's happening above the condensation point, you're probably pushing your luck as a paraglider pilot, because you're flying in cloud that's exploding upwards. The area that's sort of safe to try and aim for is this area between the ground and the cloud.
But isn't that why it's important to understand it?
Yes. Yes, exactly.
So forecasting it and actually potentially life-saving?
Yes, very good point. So yeah. But like you said, there is a reason there's curves, and it's just because there's less energy getting put back into that air to slow the cooling.
Thank you.
So this is a situation where air is what we call absolutely stable. So it's stable and unstable. Unstable being that air will just keep going. Stable means it doesn't want to keep going. But say some air's come along the ground. Sure, it hasn't been heated, but it's hit a hill and it's been lifted. It's still going to cool. It's still getting lifted. It's still expanding. It's still cooling off. It'll still cool at 3 degrees every 1,000 feet until dew point. It'll still cool at 1.5 degrees every 1,000 feet once it's condensed, to the point where it crosses its mountain. Now, say this is the mountaintop. That air that was raised by the mountain is much, much colder than the air out surrounding the mountain. So that air, once it gets up there, is going to want to come back down again. We call that stable air, air that doesn't want to rise. So this is just what it looks like on a graph. The air staying colder than the environmental lapse rate. Is that all good?
No.
Cool. If it was anybody else, it would pay attention.
If you're telling me that once it gets over the mountain it's going to drop, how does it get up there in the first place?
So think of just wind.
Wind's blowing it.
The wind might cruise along, it hits a hill, it goes up, up and over. I've actually got some pictures for that later on too. Now this is just a little bit of a visual representation of these inversions I spoke about. So air can get warmer as it goes up. Sure, it's getting heated from the ground, but sometimes air gets mixed around by storms or various things, and that warm air can get deposited on top of some cold air. And you get these things called inversions. So an inversion is an increase in temperature with height, and it's known for stopping thermals. I mentioned isotherms before, ISO being constant, so air staying the same temperature as it gets higher. Or this is the environment, so it's not getting higher, but it feels the same temperature as you measure air temperatures as you go up. Things that cause this, one can be the mountains. Mountains start mixing air around unnaturally, and it starts depositing warm air from, say, outside on top of cold air that was sitting in the bottoms of valleys. So you find in mountainous areas quite often you get these inversions where the air up higher is warmer than the ground. Fronts. So I haven't mentioned fronts yet. A front refers to a parcel of air moving horizontally over an area. Sometimes that air that's moving is hot. Sometimes that air that is moving is cold relative to the air that was sitting there waiting. So say over the top of us in Christchurch there's a bunch of air just sitting here. A bunch of warm air gets moved around by the powers that be, big weather systems. If a warm air gets moved over the top of us, it's going to come up and sit on top of us. That's called a warm front. The leading edge of that air parcel moving over us is a warm front. And a cold front is a cold parcel. And that cold front, or that cold parcel of air moving over Christchurch will slide underneath the air that's here. And the leading edge of where that's happening is a cold front. The front stuff is actually the very end of this. But I just sort of briefly mention it now because that's one way that air can become inverted. Warm air will slide up on top of cold air as it arrives from a different area due to weather systems. So it's going to look like this normally. It's warm on the ground, cold in the air. In these situations with inversions, it's normally cold at the bottom. It feels a bit warmer, but then again, it will cool down as it continues up above that. Now this is one of the last little zigzaggy pictures we have. We're nearly moving on. And this is just to demonstrate something that an environmental lapse rate can do. So disregard that this is talking about up to 12,000 metres. Just imagine this is your environmental lapse rate. It has a whole lot of different temperatures. So what you're doing is you're looking at your air and you're going, okay, the air on the ground is about this temperature, call it 15 degrees, and it's getting colder as it goes up. It becomes vertical. So a vertical unchanging temperature of air is called isothermic. And then it starts to warm up again, and that's called an inversion, that's right. So what you're going to do, you go, okay, air on the ground, it's been heated from 15 degrees to, say in this case, say it's about 20 degrees. It's going to lift and it's going to cool off. But eventually it's going to hit your environmental temperature and stop getting higher. If it heats up by an enormous amount, say it's 45 degrees hotter, this rock is just boiling and it's heating up air like crazy, that air is still going to cool, but because it got so hot at the start, it'll never cool down enough that it reaches the environmental temperature. And then it becomes an unstable lifting air mass with a really strong thermal. Say the ground was really cold, say it was snow and it was cooling the air down. If that air started to rise due to it hitting terrain, it's still going to cool, it's still going to become cloud as it gets higher and higher, but as long as it stays colder than the environmental air around the outside of it, it'll never lift on its own, it'll sink back down again. And the absolute last zigzag, this is just the nice to know. So do you remember I talked about the chopper pores where we are? Mm-hmm. That's how small we are down in the atmosphere down here. That very small strip. That's in metres there, so it's between 20 and 80,000 feet, the chopper pores, but on average it's about 36,000 feet or 12,000 metres. Above that, it does actually warm up again. So that's why the air stops. Remember we talked about air will not rise if it's warmer around it. If it stays, it'll only rise if it's warmer than the air beside it. So that's why all of the air stops here, because the air becomes isothermic in the stratosphere and actually starts to warm up. It warms up due to things like the sun hitting particles in the atmosphere, they sink down into the atmosphere and cause a couple regions where they stagnate and heat up. I'm not 100% sure, but I believe it's things like ozone.
It's more the formation of ozone. The energy from the sun splits oxygen atoms apart and they rejoin as ozone, and it gives off a lot of heat.
Yeah, so that heat, that's why we get a couple of areas in the upper atmosphere where things warm up again, have another chance to cool down, and then the actual ionized particles or something in the upper atmosphere also get hot. But this is all just for fun. It's just that the environmental laboratory does continue doing all sorts of crazy things all the way to the top of the atmosphere.
Your commercial pilots, you're flying about 7,000 metres?
Right there. We fly on the tropopause, roughly.
Right.
The weather stops there. It's a really nice place to fly. Also, the air gets colder and colder, so as it gets higher, it gets colder. Engines like that cold air and that night, because once it starts to warm up again, it's getting thin and warm, so it becomes less efficient to use. So we stop flying higher at about that point where the air starts getting hot and thin. But as long as it keeps getting colder as it gets thinner, we can still use it, and we just usually park ourselves just on top of that weather and fly around on a perfect day.
So when they get those like really heinous turbulence bits, is that just like the last bits of the thermal coming up, or?
It can be. It can also be the jet stream.
Right.
So jet stream, I very briefly touch on it at the end, but it's these giant jets of air that move around the height of the tropopause. They actually drive the planet's highs and lows, but they flow as rivers around the planet, and if you fly a plane through them, on the boundaries of them, you get shaken to shit. Get nicely in the middle of it, it's like an accelerated treadmill. It takes you where you're going, or slows you down really badly. But that's normally what it is. It's either the top of something like a front, or flying in and out of these jet streams. Anyway, we're digressing a little bit. So here we are. We've talked a whole lot about the vertical stuff. So now we're going to move on to the horizontal stuff. So wind. Who can tell me some stuff about wind? This is me trying to wake you all up again. You all know what wind is. Can anyone tell me what causes wind?
The heating of the land.
Pressure differentials.
It does have an effect, yes.
Differences in pressure.
That's the golden answer right there. So, before we go into pressure differences causing the wind, just a few basics. Wind direction is where the wind is coming from. So say you're looking out here, you're looking to the north and the wind is in your face. The wind is a northerly. Where the wind is from. Wind speed is given in a million different ways. In commercial aviation, we refer to it as in knots. In paragliding, it's normally referred to in kilometres per hour. I'm a bit of a knots guy, but I do kilometres for paragliding. The difference is about 1.8. So if you're going 100 knots, you're going about 180 kilometres an hour. But generally, you can just use about a times 2. Knots is about double kilometres. So if you're looking at a weather chart and you're like, oh, that says 20 knots, what's that in K's? Just halve it. It's the easiest way to do it. You'll come across this all the time. Yeah. That. There's twice as many K's per knot. And that blurred out bit at the bottom there, it just says knots are most common in aviation. And kilometres are most common in paragliding and non-aviation websites. So this is one of those foundation things at the start. Understanding this concept is one of those basic things you need to understand weather forecasting and things. So air will always flow from a high pressure area and try to flow to its low pressure area next to it, if it has one.
Hang on. What causes, we want to go back, what causes a high pressure area and a low pressure area in the first place?
It's actually these jet streams in the upper atmosphere. So this is something I was actually trying to avoid talking about.
Well, don't go too far into it, but I just think...
So I'm going to pull up a slide from the end of the brief. This is where are we? You asked, so we're going there.
You will not go too far.
No, we're not going too far off track. But where is it? Here. This is the planet. This is the equator, and that's the pole. Now, the equator is the part of the planet that spends the most time in the sun, so it's the hottest, right? You're all familiar with the tropics being a hot place. Tropics are about this. Pole's a very cold place. Now, we know air that gets hot will try to rise, and air that gets cooled down will try to sink. So the poles are constantly cooling down the air above it and pulling down air. Air at the equator is constantly rising, and air is coming in to replace it, and you start getting this down at the poles, up at the equator thing. Now, in a perfect world, it would go all the way like that. There is a thing called Coriolis effect that makes the air, as it moves around, start to circle. I do talk about that very shortly after the point we were at. But that just causes the air to take a little bit of a pause and start spinning the other way in the middle like an eddy. Your jet streams that drive this whole planet occur at these meeting points. So you get hot air meeting cold air. When they meet, they don't just hit. They start to rotate on top of each other. As it rotates, you get a bit of air going up, a bit of air going down. It starts to spin like water in the toilet. Well, they actually start to spin like this, and the bit in the middle starts to get driven along, and you just start getting these jets of air flowing along where these cells meet. And because there's so much air being accelerated and sped up, at some point it has to suck air into it, and somewhere it spits that air out. You don't need to know about this stuff, but it's nice to know. So those highs and those lows are just points where jet streams are sucking air in and pushing air out. And there's a whole lot of spinning and all sorts of detail going on. You don't need to know. But it's kind of fun to know. So this is a picture that represents it. This is that Hadley cell, the cell next to the equator. It goes up. Where it meets this other cell rotating in the middle, you get the jet stream. And they run, in a perfect world it would just run around the same latitude, but it kind of does a bit of a zigzag and stops and starts, depending on what's going on around the planet. So that's a jet stream. And that's what generally drives most of the weather on the planet. You're good. You've got to ask the questions when they come into your head, because that's how they stick. So,
that's optimistic.
Yeah. Now, I do apologise, this is very low definition. It's actually really hard to find a picture like this. I made this at a mine site in PNG using dial-up internet. So, yeah, it's very low definition. But basically, these two represent the northern hemisphere and these two represent the southern hemisphere. We're going to concentrate on the southern hemisphere because it's much easier to explain. If you have a high area of pressure in the southern hemisphere, it's going to try to flow out to the low pressure area, but it's also going to rotate. Rotates due to something called the Coriolis effect, which we will look at on the next slide. But it's basically a force that causes air to spin. It spins around highs in the southern hemisphere anti-clockwise. We refer to these as anticyclones, and they spin anti-clockwise. The opposite is true for a low. In a low, we call it a cyclone. It spins clockwise. So anticyclones, anti-clockwise, cyclones, clockwise. So all the while the air is trying to fly from high to low, while also spinning, and you get these outflow, inflow, zigzaggy lines. These kind of things are represented on isobaric charts. I don't really use them. With all the modern technology of 3D pictures and nice stuff, you don't really use them anymore. But you'll see these areas of highs and lows. You would have heard them on the news growing up, potentially. They're just good to know about. Areas of high pressure are generally calmer. Areas of low pressure are generally windier. Generally. So takeaways from this part here. Air does try to flow from high pressure to low pressure. That's the wind. If the pressure was strong, the wind would be strong too. So the if there's a big difference between the high pressure and the low pressure, the air will flow faster. And that gets represented by the spacings of these circles we call the isobars. Has anyone not come across an isobar or a picture like this before? You've all at least seen something like this at some point? Cool. So these isobars just represent areas where it's the constant pressure. They spiral out from a high and into a low. So that says about 1,000 hectopascals. Hectopascals being our unit for air pressure. That line is where it's constant. That's 104, gets higher, and 108, it gets higher again. If they're really far apart, there's not much pressure difference. There's not much temperature difference. The air flows pretty slowly. If they're really close together, there's a big pressure difference that air generally flows faster. You'll very rarely use this for forecasting. But it's good to know.
Why?
Because there's really easy things like windy, but you can just go, how fast is the wind here? You click it, you go, it's moving that fast.
Do you know more about what's coming in the next couple of days?
Yeah. So if you see, there's going to be some closer bars coming, that's a great way to forecast ahead. The easiest way to forecast ahead is to use like a sliding bar and go, what is it going to be on this day? And will it be fast or slow? I'm not saying that don't do this, because knowing how to look ahead and see that there's an area of high pressure or change coming, that's a great thing to do. But we screwed our atmosphere up so badly that it's really hard to forecast anything more than about 2 days out. So that's why I'm a big fan of just sort of looking ahead and going, okay, it might do that on that day. And then the next day seeing if it's actually going to do that, and then on the day of going, does it actually agree? Quite often told you fibs. So air does not flow in a straight line between high and low like I talked about. It does the circles. Tries to spin every time it tries to move out. We'll talk about that, why that is very shortly. We can almost say that wind flows along isobars. So this is a term you'll come across quite a lot. So air trying to flow from high to low generally will be in the direction of the isobar around the high. If Coriolis is strong enough, air will not fly from high to low at all. It will just try to and end up spinning in circles on itself. So that's why we say air generally follows the isobar line as opposed to out. There's a whole lot of that shortly explaining what's going on there. And that air does not spin the same way in each hemisphere. So in the northern hemisphere, it's all the opposite. You might have heard how toilets spin the wrong way up north, Europe and America. So this is still an anticyclone, but it spins clockwise in the northern hemisphere. The easiest way to differentiate it all is remember in the southern hemisphere, your highs are anticyclones, spin anti-clockwise, and then just try to work out the opposite happens in the northern hemisphere, okay?
Just referring to the isobars, for when they fly off the gondola, if you look on windy and you can see it's westerly or northeasterly, I'll then go and have a look at the isobars to see what they're saying. And if it's like there's a high and there's a huge, it's local effect. So then I'm not concerned about the northeasterly coming through. So
yes,
combine the two together to figure out, is that westerly because it's northeasterly or is it just the local?
Yeah. So what he's getting at is you can look at your forecast for the day, and if your isobars are really far apart, there's very low likelihood that things are going to change. So as you said, if things do change, it's because of a local effect, something like a little bit of sea breeze, air getting pulled in off the water due to the land heating up. But if the isobars are quite close together and he starts sensing wind, that can tell him that there's a weather system coming in and there's going to be a bigger change going on in a bigger area. So that's, very, very handy piece of information to know. When we go into forecasting, there's a method that I personally use. I'll talk about it on the night, but basically I like to look at the bigger picture first and go, what's coming? Is the day changing? And then I start going into the little nitty-gritty details. If you can all make it, on the next night we start talking about weather forecasting charts and things. I'll bring that in a bit more, but if you're in a high and those bars are far apart, things generally won't change too much. If they're close together, there's lots of things changing. Things are trying to balance out. Any questions? Cool. Now, Coriolis effect, Some people just never get this. But this is what causes all the air to spin. So imagine this big sphere, three-dimensionally out off the wall and back in again. And imagine it rotating. So we know the Earth spins. Apologies to any flat earthers. This doesn't apply to you, just block your ears. But if this is a sphere, it's going to be rotating like this, and it's going to be rotating very fast along the equator relative to the pole. So imagine you're standing on the equator. You travel a really long distance in 24 hours around the planet. But if you're standing on the pole, all you're doing is this. You're not really moving. That means all of the air stuck on the outside of the planet, very loosely stuck to the outside of the planet, is spinning with it. If due to something like that big global circulation I talked about before, air moving away from the equator or vice versa, as it moves away from the equator where it was moving really fast, it's still spinning, but now it's becoming closer to the center of the planet as it makes its way down and in. That really fast air is still spinning really fast. As it leaves the equator, it's going to try and rotate ahead of the planet. And the same applies for air that's barely moving at the bottom. As it moves up over the faster moving planet, it's going to lag behind because it can't keep up. It didn't have that energy in it to be spinning that fast. So that's why air moving south from the equator will spin ahead of the planet like this, and air moving up from the poles will lag behind the planet. Same happens in the northern hemisphere. That principle is called the Coriolis effect. The same thing happens as air rises. As air rises away from the planet, it becomes a little bit further away from the centre. It's either going to speed up or slow down as well, and that's why air rotates as it goes up and down, as well as big air masses rotate as they try to move around the planet up or down. If they were moving straight along the equator, it's just going to stay stationary, and that's why weather systems can't transition from the northern hemisphere to the southern hemisphere, because that engine that's making them spin, being the distance from the equator or north or south, can't affect it at the equator. It just stops, and as it starts moving past the equator the other way, it tries to rotate the other way, it'll just stall itself out. So that's the Coriolis effect. It's what causes all of the air on the Earth to rotate every time it tries to move sideways.
Say that again.
The Coriolis force tries to make all the air that's moving out sideways, it forces it to spin. That's just the biggest thing to take away. As air moves, it always tries to rotate. Everywhere on the planet except for that line along the equator. Coriolis effect. If that didn't stick into your head, jump on YouTube. There's some people who talk about this for 20, 30 minutes and explain it excellently with 3D pictures and all sorts. But the biggest thing to take away is just moving air will generally try to rotate. So we mentioned before, if this air is constantly flying from high to low, but it's actually rotating and never actually flying from high to low, how does it actually get there and balance out? It does that with the help of something we call surface friction. It's 8:15. I'll try and get us out of here by 9. Is that okay? The next part's the interesting part. So, air up in the atmosphere, flying from high pressure to low pressure, moves along these isobars. Imagine that being a full circle. On the ground, that air gets friction on the surface. So think like carpet burn. You run your hand along carpet, it's got a bit of friction, it's holding your hand back from sliding along. That friction will slow down that air. How much it rotates is determined by how fast it's moving. So if you can slow the air down, it finds it easier to flow from high to low pressure. The amount that it flows changes depending on the surface. So this is once again in the upper atmosphere, it's flowing pretty much 90 degrees to the isobars. In a mountainous area, where it's very rugged, it's going to flow much easier from high to low pressure. And on smooth surfaces like the ocean, snow, flat farmland, it's going to flow from high to low at a lesser rate. This isn't super important for you to know for your paragliding, but it's just, once again, another little nice to know how it actually does balance itself out in the end.
Hey Fraser, maybe we've been going an hour and a half now. Maybe we could do that thing where we split it and do one session.
I'll stop it.
My brain's getting
I'll stop it right here.
Now.
Yeah.
Because you're so cute, Simon.
Yeah, cool. So there's 3 PowerPoints. There's 3 more slides, and then that's the next section is where we have all the real world applications about what's going on around hills and thermals and stuff. So we'll stop before that and make it night number 2.
Okay. Foundation, surely you can build something out of it.
What's that, sorry?
You just stop in the point for all of us.
Well, I mean, we can go on if you want, but I'll forget it all. Yeah. I think it's better to break it up into one session.
Cool. So this is a slide from Windy, the website windy.com. This is what I use for the majority of my forecasting, be it flying big aircraft or flying paragliders, because it has like a moving model. This is just a slide of it, and I've taken this just so you can see what a high and a low look like in the real world. So that's New Zealand. This is a high pressure area. So air's getting forced down from above, and it's compressing the air here, making it higher pressure. And these isobars are spaced really far apart, so the air's moving really slowly. Now these little dashes represent the air moving. So you can see they're kind of moving around the high, but they are slightly crossing outwards as they flow outwards. Over here we have a low, and this is a really aggressive low, quite low pressure. Those isobars are really close together. In that area you're going to have a lot of wind. And you can see the air going around it clockwise, rotating into it slowly in. Not all highs are matched with a low. It's a bit sort of random. So here we have a couple of low pressure areas. They're not very aggressive lows, they're very weak, as opposed to this big low here. So they're going to interact differently with each other. Anyway, that's just what they look like in real life. This is the last part of this. After this, there's kind of not really any science, so that's all going to be the next night, by the sounds of things. Bernoulli's theorem is a concept about air pressure and air speed moving through a squeezed area, say. So what this represents is a parcel of air moving along. As that parcel of air gets compressed, it's going to speed up, like it gets squeezed through a little hole. As it comes out the other end, it expands and slows down again. This is called Bernoulli's theorem. What it actually says is the dynamic pressure and the static pressure, as in the moving pressure and the stationary pressure, will always equal a constant. If air speeds up, the pressure drops. As air slows down, the pressure rises. And this is how a wing works. That's your wing. Air moves over the top of your wing, the pressure drops, and it allows you to create lift. The reason I brought this up, you don't need to know that as a formula or anything for meteorology. The reason this is in here is so that you understand that terrain works the same as a wing. If air hits it, say it hits a hill, as it moves over it, it will compress it and it speeds up. At the top of the hill, it will be the strongest. As it goes back down the other side, it will slow down again. Same in a valley. Air goes into a valley. It gets compressed in the middle. As it moves up the valley, then once it goes out the other end, it slows back down again. So the sciencey word for that is the Bernoulli's theorem. But it's just a bit of a concept that you can apply in the next part that talks about air moving around actual objects and things. So this applies in valleys, over hills. Air can accelerate between trees, it can accelerate between buildings, even rocks on a small scale. Air will accelerate as it gets squeezed over a saddle, like at Taylor's mistake. You will know that at the gut, the air usually speeds up and flows out that saddle in the back there. That's all because of this thing called Bernoulli's theorem. As air gets squeezed, it speeds up. And it can be very, very strong. If you halve the gap, it will double the speed, essentially. And yeah, that little bit there, that is why air or wings create lift, that area above the wing. Speeding up, lower pressure, higher pressure below, creates lift on the wing. So that is the end of the science part. And yeah, this is like a break where we're going to call it, by the sounds of things, we've organised tonight for the 8th.
Yep.
So after the 8th, the night of the 8th, we'll come back and there's a few things we're going to start looking at, a little bit of a teaser, stuff like where turbulence is being created, our phone wind effect, why you get rain on the west coast, dry air on this side. This is the mathy part he was talking about, all these numbers that are kind of just fun for pictures, catabatics, sea breezes, thermals. I've got a whole lot of explaining what's going on with thermals formation and stuff. So that's the next part, but you can't really talk about any of that stuff until you go through those basics of what we spoke about tonight. So I'll just do a little recap, try and make it stick. What causes all the air on the planet to move? Sun, that's right. So if the sun's hitting the ground, remember, things start to happen generally. If the sun's not reaching the ground, generally, you don't get the same effect. You don't get the same lifting and heating. The environment gets colder from the ground up. You haven't seen the slide yet? The environment gets colder as it goes up. If the air is heated and starts to lift on its own as a parcel, an adiabatic parcel, remember it cools down really fast. That's why air doesn't generally just explode all over the planet. But if it does form cloud, it does cool slower and then sometimes it starts to run away. What else did we talk about? Yeah, I think we're done. Does anybody have any questions about any of that stuff? All of this stuff is in your PG2 content that's provided by Met Service, if you got that when you're at flight school. A lot of the stuff can be learnt using commercial pilot books. There's a Waypoint book series. There's a Meteorology book. Take you a good couple of nights to read it, but it does explain this stuff very well. There's a private, commercial, and ATPL level. Unfortunately, some of the good stuff's at the end. But there's a million other places you can go to look for this stuff. You can message me and ask me for the PowerPoint if you want it.
So I think Edmund's doing a video and he'll put the PowerPoint in the video.
There you go. Yeah.
You could.
We're done. Thanks, guys.
So as Fraser said, I've booked the hall for the 8th of July. So we'll come back and do another session there. I mean, I think if you can think about what he's talked about, maybe we can start that session with a few questions, just to recap, and then go into the next part of it. But yeah, thanks very much, Fraser. That's really good. Yeah, sweet.
Yeah, it's well done.
So we'll see you all. So that's Thursday. No, it's not. It's
Tuesday night.
Tuesday night. Yeah.
Endorsed by the old man.